Good morning, everyone. Welcome to today's webinar in the SERDP and ESTCP webinar series. My name is Jennifer Nyman. I'm a principal at Geosyntec Consultants and the facilitator for today's webinar on behalf of SERDP and ESTCP. The webinar today will consist of a brief overview of SERDP and ESTCP, followed by technical content that details results from Department of Defense funded research on accelerated corrosion and aging studies to protect weapons systems from environmental degradation. First, Mr. Jim Dante from the Southwest Research Institute will elaborate on the role of relative humidity on corrosion, galvanic interactions, coating delamination, and cracking within the context of developing an improved accelerated laboratory corrosion test. Second, Mr. Alex Lilly, in place of Dr. Victor Rodriguez-Santiago today, from the Naval Air Systems Command, will discuss the development and validation of a cyclic humidity corrosion test method. Q&A sessions for each speaker will be held at the end of their respective presentation. We will conclude today's webinar with a final Q&A session with both speakers. On slide 6, we have provided a few suggestions in case you experience difficulties with the broadcast platform. Firefox, Internet Explorer, or Edge are the most compatible browsers to use. If you lose the content on your screen, or if your screen freezes, try keying Control F5 to perform a refresh. If you're accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, please call into the conference line shown here, or you can submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties, and the Q&A option in the platform menu should be reserved for questions for the speakers. Today's broadcast will be listen only. You may submit questions by using the Q&A box that is on your screen. You do not need to submit your questions, and in fact, we encourage you to submit questions in advance of that session. When you submit your questions, please make sure to add your organization name at the end of the question so we can identify you during the Q&A sessions. And with that, I would like to introduce Dr. Kurt Preston, who is the SERDP and ESTCP Program Manager for Resource Conservation and Resiliency. Dr. Preston has tracked his career between civilian, university, and military positions. Prior to his current position with SERDP, he was a faculty member and research administrator at the University of Nebraska-Lincoln, where he led faculty development efforts to improve research competitiveness. In this position, he also worked with technology transfer personnel, academic departments, and colleges to build university research capability. In addition, Dr. Preston has served as a member of the Chief of the Army Corps of Engineers Environmental Advisory Board. Kurt?
Thank you, Jennifer. I'm happy to welcome everyone to today's SERDP and ESTCP webinar. SERDP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the Department of Defense, the Department of Energy, and the Environmental Protection Agency. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on Department of Defense requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. Next slide. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the laboratory and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs, with much of SERDP research occurring at the lab and pilot scale, with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. Next slide. There are 4 program areas in SERDP and 5 in ESTCP. The Installation, Energy, and Water program area is only found in ESTCP, while the other 4, Environmental Restoration, Munitions Response, Resource Conservation and Resiliency, and Weapon Systems and Platforms, are found both in SERDP and ESTC programs managed jointly by a designated program manager. Next slide. Our webinar today is focused on research and demonstrations that were conducted under the Weapon Systems and Platforms program area. This program area has essentially 5 major focus areas. First, surface engineering and structural materials. Second, energetic materials and munitions. Third, noise and emissions. Fourth, waste reduction and treatment in DoD operations. And finally, lead-free electronics. Next slide. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. As you can see, upcoming webinars will cover a broad range of topics, including the role of soil microbial communities in ecosystem restoration, treating emerging contaminants, new non-toxic and sustainable paints to prevent corrosion, adaptation strategies to address uncertainties around climate change, tools for vapor intrusion and mitigation, and building efficient energy and water solutions. The next WP webinar is on June 6th and will focus on developing and demonstrating non-toxic and sustainable paint to prevent corrosion. Next slide. You can find more information about upcoming webinars at this link. Registration is live for webinars through the end of the calendar year. I would like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. We would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at the end of this webcast. Next slide. I'm also pleased to announce that the SERDP ESTCP Symposium will be held again in December in Washington, D.C. The 3-day event will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration information is available on the SERDP ESTCP website. And I hope you enjoy today's webinar.
Wonderful. Thank you, Kurt. It is now my pleasure to introduce today's first speaker, Mr. Jim Dante. Mr. Dante is currently the manager of the Environmental Performance of Materials section at the Southwest Research Institute in San Antonio, Texas. He has over 25 years of experience in the field of aerospace corrosion. His work has focused on assessing the performance of materials, coatings, and other corrosion mitigation strategies under atmospheric conditions. He has worked to develop exposure techniques and metrics to accurately mimic field performance and quantify corrosion damage. Jim, please proceed.
Great. Thank you for the introduction, Jennifer. I appreciate that. I'd also like to thank SERDP and ESTCP for hosting these seminar series. And I'm looking at the number of people that have logged in today, and I just want to acknowledge and thank all of you for being there. And I think your presence here really reflects the importance of the SERDP ESTCP funded efforts to the community. So today I'm going to talk about one of the projects that we have worked on, have recently completed, WP 1673. And the goal of that project was to come up with an improved accelerated corrosion test. Now, I'm not going to talk very much about an accelerated corrosion test today. What I've decided to do instead was to talk a little bit about the interesting things that we learned along the way. And specifically what I'm going to talk about is how cycling the environment affects specific failure modes. And the reason that's important is because as you move into developing, if you want to develop cyclic tests that are better than the ones you have now, you kind of have to understand how those work in order to make things work better. So this is the agenda of what I'm going to be talking about today, a little bit on the background, some technical objectives and approach, talking about the results and some conclusions, and then benefits to DoD. Okay, so talk a little bit about hexavalent chromium, and for those of you in the paint world or the protection world, you know that chrome is a fantastic inhibitor for corrosion systems, and it's quite frequently used in paint. The problem is it's extreme carcinogen, and it's an environmental toxin, and because of that, there are increasing regulations on its use. In fact, it's supposed to be completely eliminated here pretty shortly. And so in order to move on from this point, we've got to identify new non-chrome-based systems. And that kind of work has been going on for a number of years, and but there's some limitations with that. So as you're developing coating systems, you know, it's important to understand if they're going to work on your system. And so the easiest way to do that is take components or samples, expose them outdoors at locations, and see if they work. And you're going to know whether they work or not. Problem with that approach is it's a time-consuming approach. The other thing is you can only put them in limited places. So, you know, if you want to accelerate the development of coating systems, you need some kind of screening tests. And so in the Department of Defense and in all industries for that matter, accelerated corrosion tests exist. And a number of those are available and widely used in the Department of Defense. But here's the problem. They don't fully replicate corrosion observed. And that's particularly true for multifunctional coatings, which are most of the DoD stuff, at least for external mold line. So coatings that act as barriers, but also have the ability to deliver inhibitors or metal-rich coatings to do protection. So as you start having more functionality coatings, these tests become particularly poor at defining performance. And you particularly see that when you're looking at rank order of systems. So the objective of the 1673 project was basically to create an improved accelerated test. And there was a number of goals in that. And the first was to accurately replicate corrosion damage modes. And then once we're able to accurately replicate them, we'd like to accurately rank materials performance. So we've got this wealth of data from outdoor sites. Can we get in the lab the same rank order of performance? A nice side benefit of all this would be if we know the levers to pull to control the corrosion rates and the kind of morphologies, perhaps you can develop tests where we can control the severity in those tests. So that was an important thing. But the biggest thing also here is looking at, again, these are screening tests. So if you want to reduce development time for new corrosion mitigation technologies, you've got to be able to test in something that's going to give you some general warm fuzzy that what you're doing is appropriate. So there's a number of things that we did within this effort. The first was to integrate representative sample designs. We've used a one-off sample design from Naval, which is, who were one of our team members on this program, a lap joint sample with fasteners, countersunk fasteners through that, and we had some Army replicate panels that had steel fasteners through panels as well. This is to get away from the simple put a coated panel out with a scribe in it, because where we see failures isn't always in what I'll call the field or even right next to a scribe. There's other things driving that. The other thing that we wanted to do is in this program was determine how critical environmental parameters affect corrosion and mechanical properties. And I'm going to spend the bulk of this talk talking about those. So what is it that drives it, and how and why? And then the last thing we wanted to do is, once we understood what those sort of levers are that affect severity and that affect different damage modes, can we look at what we currently do in the lab with what's going on real world field sites and get an idea of what we're missing in the test and try and fill in the gaps with that. Okay, so I'm going to start focusing on some of the results here. For those of you who want in-depth details of all the techniques that we use, I recommend, if you'd like to go read a 400-page report, to go see the report, the final report for this project. But there's also a number of publications, papers that document all the procedures in this. What I want to accomplish today is sort of a high-level picture of a number of the things that we heard, and particularly the effect of relative humidity. All right, so let me just orient you to this first figure here. What you see is on the x-axis relative humidity and then corrosion rate. So these were samples that had a matrix of sodium chloride or other droplets put on them. And you can see the corrosion rate after 1 month of exposure. And on the right, you see what are considered the ISO levels of high, moderate, low, and very low corrosion rates that you see in the field. For those of you familiar with atmospheric corrosion testing and the ISO 9223 standard, one of the things that they clearly note in there is that they believe corrosion happens at above 0 degrees and above 80%. So as you look at these corrosion rates from these steel panels, you can clearly see that there's corrosion occurring at moderate and or low levels, certainly down at 65, which is well below the deliquescence point. So deliquescence is the relative humidity at which a salt crystal will turn into a puddle of corrosive fluid, or in the case of sodium chloride, corrosive fluid. So you can see that as you drop below that point, we're still getting significant corrosion. And even down to 50%, it's not negligible, the amount of corrosion. If you look at seawater, even if you drop down to 30% relative humidity, 30 to 35% relative humidity, it's very low, but it's occurring. And part of the reason for that is because seawater contains magnesium chloride. So that magnesium chloride allows the surface to remain wet, even at very low relative humidity values. So the first point that I want to make is that you can't just say corrosion happens above 80% and doesn't happen below 80%. When we design test chambers, typically we measure wet time and dry time. Now there is some chambers specs that call out a ramp time, and that's important because corrosion happens. The other thing I want to point out is if you look at these images on the bottom as a function of relative humidity, you can see the corrosion. So there's the image and then the digitized image that was used to measure depth of attack. And you can clearly see as you go up in relative humidity, the difference in corrosion that you see. In fact, the subdeliquescence point at 70% humidity has fairly well covered the surface. So you can see its value of attack based on here. Interestingly, as you jump above that deliquescence point, you can see a distinct change in the behavior of this morphology. So there's much less corrosion, but the corrosion you do see turns out it's very deep. And the reason for that is because as you go above the deliquescence point, you get fully deliquesced salt, the droplets coalesce into a thin film. And so you have a large cathode. So instead of corrosion being driven by just what's going on around, the edge of a droplet, it can occur, the electrochemistry happens, the cathodic reactions occur at distances. So you get single or small anodes that become very deep. Okay, so sort of to summarize all of that stuff, if you just looked at magnesium chloride, you can have corrosion going on down to 11%. And if you load up enough artificial seawater in this, corrosion can happen down at 23%. Again, it's very low, but it happens. But there's a large disparity of attack. So again, corrosion happens under the deliquescence point, and the morphology and what that corrosion looks like is very different under the deliquescence point than above it. I'm going to move on to talking about aluminum alloys. Excuse me. What you see in these pictures here are images from two different exposure techniques. So this is the standard B117 continuous fog, and this is G85A5. This is the cyclic technique with much more dilute solution in there, but it's pH'd at about 5 instead of allowing it to be neutral around 6.5 to 7. So these are aluminum panels. They have a crest fastener, so a stainless fastener through the middle of these things. And you can clearly see the difference in behavior in these things from this continuous test to the cyclic test. And so one of the things that we wanted to figure out was why and what's driving this. So in a lot of the work we've done, we use multi-electrode techniques. Again, please refer to the report and the papers that were written for the discussion of this. But basically, what we had was 100. So these 10 by 10 matrices that represent the electrodes. In that, these were made out of wires that were 250 microns and close packed to each other. And this configuration, and in all these images that you see here, these 16 electrodes were made out of steel and the rest were aluminum. The other thing that I'll note is anything that you see in red here is corrosion, and anything you see in blue is a cathodic reaction. And the last thing I'll mention is that these top 5 rows of electrode were covered. And these images you see here, they're covered by tape, so nothing, they're just blocking them. And in a slide I'm going to show you later, these are actually covered by paint films. So the first thing to note is that at 60% relative humidity, just like you saw in that other previous slide, corrosion can happen on these steel electrodes. Interestingly, as you jump up to the 90% relative humidity, you start seeing these aluminum electrodes corrode, and all of these steel electrodes become cathodic. So as we've formed a continuous layer, these are now driving the corrosion reaction and become cathodic. So again, if you look at a B117, which is a continuous film of water, electrolyte on the surface, that's part of the reason you do not see this happening. If you drop down in the relative humidity again, so we've cycled up and now we're cycling back down, you can see that electrolyte layer break up and you can start seeing that aluminum corrodes again. So this is some of the raw data from those. On this axis, you see time. This is time, but what we did was scan the relative humidity, and I apologize, I don't have it in relative humidity scale. And you can see the cumulative current. So for all the red squares, we added up the currents of those. And so you can see, and this point corresponded to about 60% relative humidity, you get corrosion occurring on the steel. And as you approach deliquescence, the aluminum electrodes start to corrode as the film forms and the steel shuts off. So this is only a nodic current, again, because it becomes cathodic. And then as you go back through the drying, starting to dry it off, dropping back down through deliquescence, you see that the steel starts corroding again as the aluminum shuts off. The other thing that I'll mention about this is that we can integrate this as a function of time and measure the charge. So the charge is directly related to the amount of corrosion that's happening. And I'll just point out this data from the aluminum because the steel is on a bad scale here. But as you go through these points, you see these spikes in this data here. And basically, this is increased corrosion rate as you go through wetting and drying. So this is under more or less steady state electrolyte conditions. So why this is important is because if you're cycling tests, if you have very short wet cycles in those tests, in very short dry cycles, these surfaces may not come to some kind of steady state condition as they're passing through wetting and drying, and you end up with very high corrosion rates. And as I mentioned on the last slide, what you see as subdeliquescence corrosion can be significantly different than what you see in corrosion that occurs above the deliquescence point. All right, so this is just summarizing that. What I'll just come down here and say is that relative humidity, this suggests that relative humidity is the strongest thing governing galvanic coupling. And then again, most of that charge, there's a large amount of charge that's passed as you go from wetting to drying conditions. But even under the wetting conditions, you can clearly see that corrosion happens. But corrosion, again, does happen in galvanic couples below the deliquescence point. The next thing I'll talk about is some work that our team members from Luna Innovations had done for us in conjunction with some work that we did on this. So what we did was took small coupons, an inch, and we put through those a fastener, a steel fastener, and then we coated those with a number of coating systems, either non-chromes or chromes, or left them. And we've exposed these things to a number of cycles, which you can see down here. So let me point out a couple important facts here. That in this first cycle, you can see that we're at 90% relative humidity, and we dropped that relative humidity down to 40%. So this is a two-step cycle. We hold that at 90 for 2 hours and dry it for an hour. In the second cycle, we have the same wetting and drying time, but instead of drying it, we drop the relative humidity only to 65, so that sub-deliquescence point. But we know corrosion is still occurring. And in the last, we fully dry it, but we completely change the time of wetness. So this is the absolute time of wet in any given cycle is increased by a factor of 4. And let me point out that all of these have the same total time of wetness through the test. The other thing that I'll note is we only put salt on this once a week. This is a modified, basically the ASTM G82, so acidified salt, and we put this through this cycle. We had. That salt was only applied once a week by dipping the panels. You'll see in the next slide the kind of damage that we see. I don't have an image of the first one. I can tell you that there was delamination, but there was very little depth of the attack. So it was small depth of attack with significant delamination. The interesting thing starts happening when you start this cycle 2, where we did not fully dry it. So on the left, you see these digital images, and on the right, you see the digitized images, so actual photographs and then the digitized images. And the thing that you notice in this test is that we see this exfoliation corrosion. These red things are above the plane of the surface. So we basically significantly exfoliated the surface. So all this stuff in blue is corrosion that happened and represents, this outline of this area is where we've delaminated coating. So there's no coating here and corrosion has occurred in this area. In the third cycle, where we fully dried the sample, we again see fairly significant coating delamination, but we see very deep attack. In fact, this is a pit that you hold this up to the light, you see light coming through the sample. So the kind of attack where you see this exfoliation happens in these semi-drying conditions, but also the degree of attack that you see is a function of the total time of wetness in a given cycle. Again, these two samples saw the exact same amount of time, total time of wetness, and how we did that across the things was important. Okay, so again, corrosion morphology is affected by this time where we spend in each of these humidity regimes, above deliquescence and below. This is some work that was performed by one of my colleagues, Eric Amaka, here at Southwest Research Institute. I mentioned to you before those multi-electrodes, and this is the data, and instead of tape over those top hats, we had coating. The idea was that we'd expose these to chambers, we'd leach inhibitors out, and either protect or not protect electrodes. So it orients you to this slide. This is time on this axis. It's a cumulative current. So again, for each point of time, we added up the currents and then added them for the cycles. On this axis, you see the relative humidity. Here's the relative humidity cycle we did. And we actually ran 2 cycles. So to make this more or less easier to understand, both of those cycles show up on this plot. And I'll talk about each one individually. The point I want to make, though, is that we added up the current for each cycles individually, okay? So this is not cycle 1, and then I add cycle 2 on it. This is just the current in each cycle. So the first thing I want to point out to you is the solid black curve. This is a coupon with no coating system on it. And you can see that that current increases as we go up and down. And as you're going in the up and in the high humidities, you can see this corrosion cumulative current increasing. And then as we dry off, it stops. So the chromate coating under the same conditions is here, this gold curve, and you can see the big knockdown factor. Now, if you're a manufacturer of the non-chrome coating and you looked at this data, you'd be pretty disappointed because, you would say, oh my gosh, this is as bad. And if you didn't care about statistics, you would say, oh my gosh, this is worse. But basically for the purpose of this talk, we'll say it looks like nothing's happening. However, if you run a second cycle, different things start to happen. So this dash curve is the bare. You see that there's really not much of an effect. As we move to the chromated coating system, you can see again that even during the second cycle of wetting and drying, we have a big knockdown factor in corrosion. In fact, it even looks better than the first cycle. And then as the non-chrome folks, you see that here you do get a knockdown factor. So this points out a couple of important things. And the first is that it takes time. There's a number of different kinetic processes that are going on here. First, there's the time for moisture to get into a coating system. Then there's the time for those inhibitors to be liberated and get out to an unprotected place. And then there's the effectiveness of the inhibitor. So in the case of a chromate, where you barely need any chromate to protect the scribe, in the first cycle you see a major effect. For the non-chromes, because they're less effective inhibitors, you need more time. So, and this may explain some of the phenomena that we see, in accelerated corrosion with non-chromes. There always seems to be some staining in this in the scribe, and this is particularly true for accelerated corrosion tests. Okay. So to summarize that, there's, looking at the cumulative currents, you see these big knockdowns. So you need some kind of initial wetting or some wetting that goes on before you can release these inhibitors, and then you protect the surface during subsequent wetting. And this just kind of quantifies that a little bit. You can see in this last row here, this is just a knockdown factor from the first and the second cycle. And so you can see that both for chromate and non-chromate coatings, class N coatings, that you see this. But it's particularly interesting to look at this row here, the total that's been knocked down from the original amount. So in the case of a chrome coating, we're only about 10 to 15% of the cumulative currents passed for chrome coating, and only about half the currents passed. So you here again, you can see that how much more effective chrome is as an inhibitor to these non-chromes. Okay, next thing we wanted to look at was intergranular corrosion, stress corrosion cracking. This data is also from Luna Innovations, the team members there. To orient you, this is relative humidity, this is crack growth rate, and what we did was cycled the relative humidity going both directions. So Luna has developed some pretty nice sensors for measuring crack growth rates in situ. And what you see here is that as you cycle the relative humidity forwards, you're on these set of curves. As you cycle it backwards, you're on these set of curves. The point that I want to make here is you cycle these things backwards, you can see that once you're in this, again, subdeliquescence region where we see exfoliation, where we see corrosion still occurring, you get large increases in the crack growth rate. And in this example here, these increases in growth rate become more severe the longer you run the test. I'll note that also these things are a strong function of the solution chemistry, so pH and what you do. So if you were to run this in a G85A5 versus an A2, you get significant differences in behavior. Let me note that, so this is data from the G85A5, so the dilute chloride and pH of about 5. And you might say, oh, well, this is a sensitized, and this is a pretty highly sensitized 5000 series alloy. But we've done, and Luna has done work on 7000 series alloys, and you still see the same kind of effect. In fact, up to a factor of 10 if you're looking at some of the fatigue data that's not shown in here from other work that we know. So both the chemistry and cycling the RH strongly affect what's going on at cracking as you dry. Also mentioned exfoliation. So a portion of this program, we had samples exposed outside. These are images of down a fastener hole. So this is actually from Point Judith, which is an industrial coastal site that Alcoa owns. So what you're looking at is the edge of the 7000 series aluminum. What would have been here would have been a fastener, and you can clearly see the significant amount of intergranular corrosion going on in here. So this was a panel exposed by colleagues at AMCOM. Oh, I'm getting that right. That did these, and you look at that same sample, you see this intergranular corrosion in here. And this was just a separate sample that we had and exposed it to an environment that was developed at the University of Virginia, and it's very close to the ASTM G85A2. The cycles are a little bit shorter. The main difference between these two environments is that the pH in here is dropped to about a function of 3. Now let me note that you do not see any of this intergranular corrosion at all if you just put this in a B117. So the two things important: number one, you need cycles to imitate this, and if you want to drive it faster, you can change the pH in the solution. Okay, so again, we think this middle relative humidity ranges, moving into this accelerates exfoliation, accelerates intergranular corrosion. We think the intergranular corrosion is actually partly related to what's driving the increase of crack growth rates during drying cycles. You see the corrosion happens, and clearly the morphology, and it strongly affects delamination. All right, so that's important. This is a little bit of an eye chart, and I do not expect you to read all this, but I wanted to point out a couple of things. So we ran some of these tests outdoors, and what we wanted to do is kind of block out the times, the percentage of times that in each environment we spent in specific regimes of relative humidity. So for these outdoor samples, you can see that they're between 40 and 50% relative humidity. And you can see the times above the deliquescence point. Sorry, this is the percentage of time above deliquescence, and this is percentage of the time, you know, in that sub-deliquescence but corrosion, so above 50%, and then this is below. And what we can do is start comparing these to what you see in the rest of these. These are marked as green because this is what you see as aggressive corrosion outside. And you can see our laboratory tests, these are marked in red. Some of these things are really aggressive, and you saw some of the images from that. So just to kind of summarize these things, you know, we know that we've got to have cyclic humidity. If we don't have it, we don't fire off these separate modes that we see in the real world, like I showed you in Port Judah. And the other thing that we know from the real world tests is if you want aggressive environments, you got to be above 50% relative, or above the deliquescence point 50% of the time. In terms of coating delamination, it's a strong function of the time of wetness within a given cycle. So I showed that to you before. Not only did we see the degree of attack change, the amount of corrosion change. I'll show you that a little bit on the next slide. So in this figure here, you can see the total time of wetness in each of these categories. These are during wetting and drying in those intermediate ranges. These red bars here represent the sum of these two. The important thing to note is these are the aggressive environments with their high percentage of time. But again, it's the amount of time in each cycle that's important, right? So if you have a complex coating system, like I mentioned before, and showed on the data that Erica Maka had done, you need a certain amount of time before you can activate inhibitors, or in the case of metal-rich primers, a certain amount of moisture has to ingress before you can see the get these galvanic effects that you're looking for. So again, this is an important thing to consider as we're doing tests. So these actually came from sensor data that has been out in the world. And so for those of you that don't know, there's other programs funded by both the Navy and the Air Force that have multiple sensors out at multiple locations, so gathering large amounts of data on this. So here's the interesting thing, though. If you look closely at that table, it's not simply a matter of just the time in the wet cycle. It's a matter of the solution aggressiveness. So in some of the solutions, we actually had very low wet time, but the solution was extremely aggressive. And so there's this trade-off between the aggressiveness of the salt solution on the surface with the time of absolute wetness. This is just a couple examples, and this I'm just looking at surface delamination from those two of the cycles I had mentioned before. So both of these fully dry, but in cycle 3 is much more the much longer time in the cycles. And I just want to point out here that you can see that the amount of surface delamination, so this is basically coating peeling off the surface, is greater the longer that time that I have in any given wet cycle, even again for the same total time of wetness. But because of the aggressiveness of that tack, which is directly related to coating delamination, in this more aggressive environment, you can see that this may be one of the tools we have. At 500 hours, we can distinguish coating performance. Whereas if those of you who run salt fog, you can run it for 3,000 hours and not see any difference. So what are the things that drive aggressiveness of solution is the pH. I showed that in a number of cases. Obviously increases salt deposition because it increases the surface area and taxes inhibitors more. And then the other thing is the amount of time above the deliquescence point, as I demonstrated here. All right, so with that, I'm going to just start to conclude here. So the single probably most relevant factor here in atmospheric corrosion is the relative humidity, but it's not simply the relative humidity, it's specific regimes of the relative humidity. And if we want to accurately replicate stuff, we can't just say, oh, well, ramp time this much. We've got to ensure that we strictly control that. And this is well known here, but atmospheric chemistry plays a large role, pH and the salts, the amount of salts, and that's got to be balanced with the relative humidity in our accelerated test as we move forward, trying to find something better than this. Just to show you that middle point when I say strict control, this is some data that have been funded by the Air Force from a program Luna had. So if you put sensors in a chamber and you monitor these temperature and relative humidity as you cycle through, each of these chambers has a certain footprint. And just to show you that these are 4 reputable labs that have done this, and you can see we all follow the specs well, but our chambers didn't obey, or well, they just work the way they work. So you wet for so much time, you dry for so much time, and hope you get the ramp rate. But how it gets from one place to the next is completely different. So again, this stresses the importance of being able to define specific regimes of relative humidity. So the next steps, and Alex will be talking a little bit about this later, is a follow-on ESTCP program to help finalize these. So benefits to the Department of Defense, developing these improved standard protocols. So, what do we do to have some assurance in this as we develop more stuff and make decisions whether we take things to long-term field testing or not, and or put on aircraft. So we can more accurately predict corrosion, again, reduce rejection of promising new technologies, right? So we reject things at the lab stage that look really good in the field. The opposite is true too. We let things through these screening tests, we put them in the field and they fail miserably. And then the ultimate goal of this thing is to reduce the use of carcinogenic materials, not just in the paints themselves, but in the cleaning processes and all that afterwards. So as I finish up here, I just want to acknowledge all the folks that took part in this. It's a nice combination of work by industry, government, our government lab partners, and universities also in the mix here. This was fun to wrestle through the program, but I think we've learned a lot of nice stuff. And with that, I am going to conclude. You can see that there's information. You can find the final report on the page. So with that, I will thank you for your time and hand it back to Jennifer.
Thank you, Jim. Excellent presentation. At this time, I would like to remind our audience that if you have specific questions for Jim, please do submit those at this time using the Q&A function as part of the broadcast platform. So Jim, we have received a few questions already. The first question is about slide 28, which was a graph about the relative humidity effect on inhibitor release. And the clarification question was, what is the salt used in that test? And was that
so that's a good question, and obviously this graph will change slightly, at least in terms of the overall amount. But for this testing, it was just sodium chloride.
Okay, thank you. What has been done to transition this work to accelerated corrosion testing?
So let me just also reiterate that I did mention we have a follow-on program that's coming to this. So that program has in fact, it's being led by NavAir. Alex and Victor are taking the lead on that with numerous government partners from the Air Force and the Army, both ARL and AMCOM. So that's from internal. This is, we've worked closely with them as we've gone through this first. So developing these final test protocols is underway and moving into round robin. The other thing that's going on is that we have engaged with some of the standards organization, in this case, particularly NACE, and this was based on discussions with our military counterparts. Where's the potentially easiest way to introduce this into a specification? Pretty extensive conversation. So the idea is that we would move this into a NACE standard. So before we do that, we have to have round robin testing. It's also been introduced at NACE, so NACE is aware of it. just waiting for the ESTCP program to turn on and fully engaging that process, the standard. So moving forward in that direction. And whether it turns into a mill standard from that, my understanding is it's easier to go that way than come up with from a mill standard first. But I'll also note that one of the advantages of going through NACE is that there's multi-industry buy-in. So it turns out that that the Department of Defense and company aren't the only guys really interested in this. If you look across industrial sectors with the pipeline world, you know, for oil and gas, for the automotive world, the questions that we've wrestled with over the last 2 or 3 decades are the same questions that they wrestle with. And so moving this, you know, allowing, you know, SERDP's efforts in this have potentially broad effects to those industries. And again, that's, you know, getting insight from them as we develop a spec forward is important. So another reason for going through NACE. So I hope that answers the question.
Yes, absolutely. Thank you. And we have time for just one more question. Why is crack growth rate accelerated during drying events, and is this something to worry about?
Yeah, that's probably a harder question to answer than any of us think, and it's actually the subject of research by a number of folks from a number of universities, us, a number of other companies like Luna Innovations and SAFE Incorporated. So the question is interesting. My personal feeling, and actually I think Luna has published a paper on this in the not too distant past, that it has to do with the fact you dry a surface out, but the crack tip does not dry out. So so you change the reactions going on from a surface. So you no longer have bulk pitting, which tends to blunt a crack, but an acidified environment, either in an intergranular site or somewhere at the crack tip, that drives a different mechanism of corrosion that's very localized. So that's my feeling. Now, whether it's important or not, that's another question, you know, because eventually, you know, the guys that really care about this are the ASIP community, Aircraft Structural Integrity Program, and the Navy guys that worry about this, you know, anybody dealing with a damage tolerance approach. So, you know, the short answer is, well, nobody's really worried about it because things have worked just dandy. The problem is, now that we're moving away from chrome, can we assess the risk of changing from chromes to non-chromes on this crack growth rate, and will that affect an ASIP or a damage tolerance type approach to cracking? And the answer is nobody really knows, because we have the data we have. So so the other thing to worry about is that the fleet is aging, so it behaves, you know, different now than it you know, did when materials were new and not ground out and all sorts of patches and band-aids put on it. So, you know, the first question is, how is crack growth rate in these wetting and drying changes as you go to new coating systems? And then the second thing, do we even care? And what I mean by that is that you could see that, you know, the degree of cracking is a function of the amount of time it spends wet and the amount of time it spends in the environment dropping back through that, as well as, you know, the amount of salt in you know, that can get in those spaces. So those are ongoing questions right now that we feel, and a number of us feel, need to be addressed moving forward.
Okay, thank you very much, Jim. And I'll remind our audience that Jim will return for an additional Q&A session with both speakers at the end of the webinar today. So if you have additional questions for Jim, just indicate that in the question and answer box. We'll now move to our second speaker, who is Mr. Lilly, a chemical engineer for the Materials Engineering Division at Naval in Maryland. He has a bachelor's degree in chemical engineering from the University of Maryland, Baltimore County. Since joining Naval, he has worked on the synthesis of and electroplating from ionic liquids, and he currently supports the development and validation of a cyclic humidity corrosion test under Dr. Victor Rodriguez-Santiago. who is the head of the Corrosion and Wear branch of the Materials Engineering Division at NAVAIR. Dr. Rodriguez-Santiago was unable to make it today, so we're very grateful to Mr. Lilly for stepping in. Mr. Lilly, please proceed. Thank you.
Thanks, Jennifer. Thank you very much for having Jim and I on to talk about our projects. As I go through these slides, I do want to mention that a lot of what we're talking about with this project, which is WP 5087, is a follow-on effort to a lot of the same concepts that Jim mentioned previously, a part of WP 1673. So on the agenda, you can see we will talk about the benefits to DoD, some background. A big part of this will be about dynamic monitoring, and then the technical approach that we're taking to sort of address and succeed with the development and validation of a cyclic humidity corrosion test. Slide 43, please. So like Jim mentioned many times, a lot of the traditional accelerated corrosion tests that we have currently are not representative for the type or severity of corrosion that we see in the field. And when I say type of corrosion that we see in the field, I mean, are we seeing pitting or coating delamination or exfoliation corrosion? Are they failing in the same way that we would expect to see them operate in the operational environment? And there's many different reasons for that, and we hope to try to address that with this project. And I'll get to sort of how we're going to do that later on. Another issue is that we see lots of chamber inconsistencies. I don't remember if you can recall that graph presented by Jim just a few slides ago with the different temperature and relative humidity cycles performed by many different operators, but very few of them were similar, and some of them were even different test to test. And so that's another aspect of this project that we're hoping to address, which is just the variability and repeatability of ACT in general. Another aspect of why those current ACTs do not perform well is their lack of control in relative humidity. So with this project, we hope to be able to design a test that calls out specific humidity, relative humidities that need to be reached at specific time intervals, rather than sort of what's currently occurring, which is 100% relative humidity for a certain amount of time, then followed by a drying period, et cetera. We want to sort of control that more specifically as it relates to the deliquescence, relative humidity, and those regimes. Slide 44, please. So what can we do to address those issues? First of all, we want to be able to understand the individual and combined factors that relate to the mechanisms and severity of corrosion. I would actually like to correct, rather than saying mechanisms for corrosion, I would like to say the type of corrosion that we're observing. And we're doing that by controlling a few different factors, one of which could be just the relative humidity that we are operating the test at, or the ratio for wetting and drying times to control things like crack growth that Jim mentioned earlier, as well as solution chemistry. We like to implement some more representative solution chemistries that are applicable to sort of what we would see in the operational environment. We also want to understand better, or we're able to understand better, the dynamic effects of the environment on how that can play in the type and severity of corrosion as well. And so when I speak about dynamic effects, what I mean is day to day, hour to hour, how is the temperature and humidity changing, and how does that affect the type and severity of corrosion that we observe? Slide 45, please. So more about dynamic monitoring. What is currently being done for most corrosion testing, the best way to observe the way a coating or new corrosion prevention technology will perform, or how that coating technology ranks against what's currently out there, is we deploy these test coupons in actual operational environments for sometimes 1, 2, or 3 years at a time. And so with this, we basically only have 2 data points, which is how the samples were deployed and what condition were they deployed, and after we go and retrieve them, what's the condition at that point. And so that's what we are talking about when we say cumulative data only. We have very little information about what is occurring day to day, how the corrosion is progressing, or how are the failure mechanisms progressing day to day, what is causing those failures. And so what we'd like to do is figure out better ways to measure that data and quantify corrosion severity over the exposure period of your outdoor field exposure. Like Jim mentioned, these outdoor field exposures are very time consuming, not very widely accessible. They can only go in certain places. And so we want to try to fix this issue and see how that will impact the design of new accelerated corrosion tests. Slide 46, please. There we go. So to do this, we employ these Luna sensors, which have the ability to record temperature, relative humidity, and solution resistance across this gold interdigitated electrode. Solution resistance is a very important part of this dynamic monitoring because it tells us when a conductive electrolyte is present on the surface. The presence of a conductive electrolyte can be extrapolated to indicate the presence of a corrosive environment. So these sensors often, well, what we've done so far is to deploy these with mass loss coupons, aluminum and steel coupons, to sort of measure the temperature and humidity, sometimes hour by hour, sometimes I think the lowest data recording limit is about every 5 minutes. And we do these for very long periods of time so that we can get a good idea about what exactly these mass loss coupons were exposed to in terms of temperature and humidity, and how we can correlate that mass loss to what we're seeing with the solution resistance measurements. What we've been able to do is develop a statistical analysis tool to quantify the relationship between solution resistance and absolute humidity in order to assess the overall environmental corrosion severity for a given exposure. Slide 47, please. What's currently used to assess environmental corrosion severity is ISO 9223. This classification looks at 3 key factors, which are time of wetness, deposition rate of chlorides, and SO2 concentration. The main issue with this method of classification is the distinction of a wet environment being only greater than 80% relative humidity and greater than 0 degrees Celsius in terms of temperature. We've collected data that shows you can have wetness events below this relative humidity, and that's all very closely related to the geometry of your corrosion that's going on, as well as the salt species that are present as well. And so a lot of what we want to be able to do is quantify the time of wetness and make a distinction about how this severity classification fails to accurately assess time of wetness. Slide 48, please. So back to the sensors. Like I said, surface temperature, relative humidity, and solution resistance shown here on the y-axis of each of these graphs can be measured at any time interval over the exposure duration of the sensor. So this is a typical output of what we would expect to see with these sensors. As you can see, for the relative humidity, there's large amounts of variability, even day to day, which revealed to be sort of a very important factor in terms of what we're thinking about when we're designing new accelerated corrosion testing. Like Jim mentioned before, the cycling of relative humidity plays a very large role in the way and the severity to which corrosion can occur. If you look at the surface temperature graph, you can also see a record of changes in seasonal conditions as well. So with this, we get a really good picture of what exactly the system was exposed to. On the rightmost curve, you can see the solution resistance data, and you can see there's also a very distinct regime of where we have high solution resistances or low solution resistances. High solution resistances would correspond to events that are dry or that there is no presence of a conductive electrolyte. And so we'd expect those data points to be more or less very low in corrosion severity, whereas the wet data points correspond to the presence of conductive electrolyte and therefore are corrosion prone events. Slide 49, please. So we can take temperature and relative humidity data and calculate absolute humidity. We found that this calculation was a crucial step in terms of finding a strong correlation between the temperature and humidity data along with the solution resistance data. So we can apply statistical methodologies that were developed by Cosima, Boswell-Kohler, as well as Dr. Victor Rodriguez-Santiago here at Naval, to sort of get a better idea about how many dry versus semi-wet versus wet data points a system can be exposed to. With this knowledge, we can also assess the exact corrosion. We can actually fairly accurately predict corrosion mass loss amounts for aluminum and steel samples, and we'll get into that a little bit later as well. Slide 50, please. So where this fits in the overall scheme of ACT development is we can use, like you see on the left, mass loss coupons along with our dynamic monitoring sensors. We can then analyze that data to capture the sort of temperature and relative humidity cycling that we're seeing in the operational environment, what that means in terms of the number of dry versus semi-wet versus wet data that we're measuring, and we can use that information to inform new accelerated corrosion testing. And theoretically, this could be used based on sort of geographical or different operational environments to say that we can design accelerated corrosion tests sort of specific to the operational environment. In the table below, I would like to point out the most important column here is the rightmost column, where using accelerated corrosion testing with this methodology, we've been able to replicate 4/9 the amount of mass loss in about 1/30 the amount of time for aluminum 70-75, and about 1/4 of the mass loss in 1/30 of the time for 10-20 carbon steel. And so this is significant in that the main goal, obviously, is to provide representative corrosion in the form of an accelerated corrosion test so that we don't have to rely on outdoor field testing, which obviously takes a long amount of time to qualify or validate new corrosion prevention technologies. Slide 51, please. So we've identified these three parameters to be the main parameters that we can tune to change either the attack morphology or the degree of attack. And so we're using this information, which a lot of which was provided during WP 1673 to sort of design and test our new accelerated corrosion test methods with this effort. Slide 52, please. So the innovative technical approach for this is that we're relying on the cyclic variation, which is informed by both by previous research and as well as data collected from the operational environment. Cyclic variation of relative humidity, as well as the salt deposition of specified salt solutions. As I mentioned before, traditional cyclic tests cannot provide this degree of control for relative humidity, and we've seen lots of, we've been able to see a large amount of variation in results from these tests as well. A lot of this understanding has been gained within the last 5 or 6 years, and so we feel we are sort of on the forefront in terms of developing this technology. Slide 53, please. So task 1 for this effort is to test a total of 6 different environments. And how we've split those up so far is to test 2 solution chemistries and 3 relative humidity cycles. This will be done mainly to identify what are the controlling chemical species in the solution chemistries that sort of mandate or offer different corrosion severity or attack morphologies. Also, the 3 relative humidity cycles will do the same, and hopefully we'll be able to get a better idea about what exact parameters in terms of the relative humidity cycles control those the mode and extent of corrosion that we're seeing. Slide 54, please. So we're planning to assess the corrosion type and severity using optical profilometry. And then after that, we're planning to rank coating performance and environmental severity using that image analysis. At the end of this task, we will reach a go, no-go decision based on whether or not we've been able to correlate and provide representative corrosion types and extents that we can see in outdoor field exposure, but at 1,000 hours of accelerated corrosion testing. And that the results from this accelerated corrosion test provide an ordinal ranking of coatings that we would also provide using outdoor field exposure. Next slide, please. Test 2 will be round robin testing, again, to address the variability and lack of repeatability that we see with current accelerated corrosion testing. This is going to be completed by a number of different laboratories: Naval, Southwest Research Institute, Boeing, Army Research Lab, AMCOM, AFRL, AFL-CMC, as well as QLab, who is the manufacturer of the corrosion test chambers that allow us to have tight control on those relative humidities. The results from this test method will then feed into task 3, which is the development of a NACE laboratory accelerated corrosion test standard. Slide 56, please. As Jim addressed in the previous Q&A session, we decided to pursue a NACE standard because of the collaboration offered by OEMs in terms of the development and drafting of the standard, which will make it easier for stakeholders such as Naval later on when we're trying to implement these test methods in our acquisition programs. So we'll really aim to reduce the resistance to acceptance later on. The other pro to a NACE standard over a MIL standard is that these standards can be revised every 3 to 5 years, which will allow for the addition of amendments to the annex of this standard or changes as operational environments and new corrosion testing requirements become available. Another thing is it should be easier to convert a NACE standard to a MIL standard later on down the line if that becomes something that is needed. Slide 57, please. We're also planning to create a NACE task group within SGG 41 to develop this specification. How we view the specification being written is the front end will define the overall testing approach, and then as new operational environments are required, we can add those amended test cycles to the annex of the specification, such that we're producing a standard that can grow as the demands of the aviation industry change or additional operational environments come up. Slide 58, please. So to wrap up, dynamic environmental monitoring devices, as well as data analysis methodologies, allow us to correlate environmental conditions and corrosion severity. Again, we did that with dynamic monitoring sensors, which capture temperature, relative humidity, and solution resistance, which allows us to much more accurately quantify the exposure, the environmental exposure of any outdoor field exposure samples, so that we do a better job of replicating those same conditions during accelerated corrosion test development. Also, we plan to observe more the combination of effects observed from varying solution chemistries, time of wetness, and drying to wetting time ratios, so that we can fully tune corrosion severity as well as control better the method of attack during those tests, so that they're more representative of what we would see in the operational environment. Slide 59, please. We also plan to assess corrosion severity and type of corrosion using 3D image analysis, optical profilometry. This will allow us to have a better quantifiable way to assess the type and extent of corrosion. Overall, our plan is to develop a more representative and reliable accelerated corrosion test standard through inter-laboratory collaboration. Again, we're doing this through round-robin testing to sort of address the issue with current accelerated corrosion tests in their variability, both between labs and between tests. Slide 60, please. The benefits to the Department of Defense are mainly to identify, to accurately identify new corrosion prevention technologies. Like Jim mentioned earlier, there are times where corrosion prevention technologies fail in accelerated corrosion test methods that otherwise perform well in the operational environment, and the vice versa is true as well. And so we want to have better testing so that we don't waste time or waste time with technologies that don't offer the corrosion prevention that we need, as well as get the technologies that do offer corrosion prevention out to the fleet. This also will help us understand risk better than what we currently are able to do with accelerated corrosion testing, in that if we're confident in the type and severity of corrosion that we're observing during ACT is representative of that in the operational environment, we'll then be able to make better statements in terms of what the risks are associated with new corrosion prevention technologies. Now that we are hoping to provide a better accelerated corrosion test, we won't have to rely on outdoor field exposures, which will then reduce testing costs. Also, the time span that we're looking to build these test methods are only to about 1,000 hours, whereas typical ACT can go towards around 2,000 hours. Overall, we're hoping to introduce better technologies faster and more reliably. And I think that's all I have.
Wonderful. Thank you so much for the excellent presentation. We have received a couple of questions. Again, I'll remind our audience, if you have questions for Alex about this work, please do submit it using the platform and the Q&A box. So first, could you explain the connection between this project and SERDP and ESTCP's initiative to reduce the generation of hazardous materials?
Sure. So our main goal with the generation of the development of this test method is to more reliably and quickly qualify, validate new corrosion prevention technologies. And with the emergence of the regulation of hexavalent chromium, we're anticipating this demand to sort of increase very much so. And so with this, we're hoping we provide a tool to the aviation industry to incentivize the development of non-chrome materials, which I believe the reduction in hazardous processes was one of the ESTCP initiatives.
Okay, thank you. Are the dynamic environmental monitoring devices commercially available? And if so, where can they be purchased?
I know that they are produced by Luna Innovations, which I believe that would be commercially available, but I am not 100% certain on that.
Okay, thank you. In the lunar sensor, solution resistance depends on electrolyte concentration and thickness. So the corrosion rate is a function of concentration and thickness. Do these effects need to be separated?
So what we do primarily with the solution resistance measurement is it allows us to indicate the presence of that electrolyte. So we're less concerned about with the film thickness and the solution concentration, and more so just that there's a conductive electrolyte present. Using that statistical analysis that I spoke about earlier, we're able to designate what times and the amount of times, the ratio of wetting and drying times the system was exposed to, which offers more information than previously offered by typical just cumulative monitoring using mass loss coupons. And so maybe to answer the question more specifically, we use this to identify wet versus semi-wet versus dry events, which then gives us a relative idea about the corrosivity of that environment over the exposure duration.
Okay, thank you. And we have one more question before we bring Jim back. What considerations were made when choosing the sample configurations to be tested in this project?
So I think Jim mentioned a little bit in his presentation, but what we're planning to use is a lap joint configuration made of dissimilar metals. So we'll have 2 panels that are of dissimilar metals. We'll also have 6 fasteners fastening those 2 panels together with 2 sets of 3 different alloys. And those alloys are common steel fasteners that we observe in naval aviation. We also have representative coating schemes to what we would see in naval aviation as well. And so there's lots of aspects to those sample configurations that are representative of the what we actually see in the operational environment. With a lap joint, we're making that crevice that is present in many different places on the aircraft, as well as the galvanic couple between all of those dissimilar metals. And so we think that we're doing a better job of producing a representative test sample, especially compared to the flat just panels with coatings or sometimes just bare. So.
Okay, thank you very much. And at this time, we will bring Jim back for a couple of final broader questions. So first, and maybe we'll start with Jim, and then if Alex wants to add anything additional, is there a target date for finalizing and rolling out the new testing protocols? And along the way, is there a place for interested audience members to go to get updated information?
So the time frame question is a little bit tricky. So as Alex mentioned, within the program that's just about to get underway, we have what we're trying to do in task 1 is based on everything we know, and it's not just from 1673, but from a number of programs. What are the environment? What are the levers that we want to see to replicate that? Okay, so if we can replicate the damage that we've observed from the fielded samples from the SERDP program, we feel pretty confident that we can then start moving into the round robin testing, and that's labeled as a go no go. So at a minimum, you know, even to move into the round robin portion of this, we've got about a year of testing worth. And of course, if we can't replicate it, I guess the program ends and then you don't get another spec. But we think we can do it, and based on stuff we've seen, is that we're fighting against chamber capabilities in this case. But I think we're going to be able to overcome that. So after that, the round robin testing is about a year. I think by the time we get through that, and then it's just a function of wrestling things through a standards body. So, like I've mentioned, we've started laying the groundwork for that. People are aware that we announced in a TEG 189X atmospheric corrosion for NACE last year. Victor gave a presentation talking about the desire to move in that direction. It was not brought up this year, but so once we've got the environment defined in a year, then we start writing the document, and hopefully by the time that document's out, we've got round robin test data that supports repeatability onto that, and then the wrangling starts. So I'm figuring probably 2.5, 3 years, and it is just going to depend upon how cantankerous we all feel about this at the end, but a minimum 2.5 to 3 years. Now for updates, so we tend to present stuff at conferences, and obviously since this would be coming through NACE, this stuff will be published through NACE, and it'll also come through the DoD conferences. They're every other year. NACE is every year. There's also the possibility NACE has off-cycle, not the big conference, but Corrosion Technology Week, and so getting information out during that, particularly after we start the process of the specification, so it'll be available then. And then I think quarterly reports are actually, I don't know how accessible they are to the public, but since SERDP ESTCP is everything is public, there's probably a mechanism to get that out there, to get people updated.
Okay, perfect. Thank you, Jim. Alex, anything to add to that?
No, I think Jim pretty much said everything I was planning to say. The mechanism for providing updates to the public, I am not sure, but that is something I plan to take back and see what we can do with that.
Okay, fabulous. Thank you so much. And as we conclude today's webinar, I'd like to ask our speakers, what's the final message you would like to leave our audience with today? And Alex, maybe we'll start with you this time.
Sure. So I think the main message is that currently we cannot rely on accelerated corrosion testing to provide representative rankings of coatings or any sort of corrosion prevention technologies in terms of making them representative to outdoor field exposure. And so what this project aims to do is to develop a more representative and reliable accelerated corrosion test to do just that.
Okay, thank you very much. And Jim?
Yeah, so I was in an email conversation with a friend and colleague yesterday who had found out about this seminar today, and he mentioned frequently in his emails that, yeah, this is the holy grail, and I just want to reiterate that he's not joking. This is, there's a lot of accelerated tests out there, and this is not an easy thing. A number of industries have tried to attack this problem, and I just want to say that the tests that are out there were not just sort of haphazardly slapped together. It's a lot of smart people trying to get their arms around a really difficult thing, and I think so our place in this is just the next sort of step along the way of how this is going, and with some of the tools that we've had access to and developed in is allowed us to have a little bit more insight, sort of to bring this to the next level. Will we get it perfect? Probably not. Will we get a lot better? The answer to that is I think that we can do that, and the next critical step is pushing chambers to the point to control things that we know are important, at least for aerospace coatings, to move in that next direction. So to summarize that, this was hard. A lot of smart people working on it, and we've just taken the next step, and I think we're making good progress in that direction.
Wonderful. Thank you both very much for the concluding remarks and the excellent presentations today. As we conclude, I would like to let our audience know that our next webinar in the SERDP and ESTCP webinar series is on Thursday, May 9th, and it will be on the role of soil microbial communities in ecosystem restoration. Registration is open for this webinar, so please visit the webinar webpage at SERDP and ESTCP to register for this and all the other 2019 webinars. And before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. And we would appreciate it if you would please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you.